Hey there, physics students. We're back with another episode of Rapid Review for Honors Physics. Today I want to summarize everything we've learned so far in motion because we've covered a lot. If you look at this poster, and you may have seen something similar in your classroom, we learned a lot about vocabulary and equations and the meaning of plus and minus and graphs. We've covered a lot. Let's take each one of those in turn. Okay, so in terms of our vocabulary, we know what a scalar and a vector are. We know that examples of scalars are distance and speed. Examples of vectors are position, displacement, and velocity. And even acceleration is a vector. I looked around. I don't think there's a special name for acceleration as a scalar, but I guess if you put the magnitude signs on that, you could say that's the magnitude of acceleration, and we don't have a special word for it like we do for speed. Okay, so definition of position and displacement, we understand it has to do with what you're measuring compared to, right? So position is compared to our coordinate system, and displacement is compared to where we started. For velocity, well, actually, let me finish here also about why I'm using X. That's my letter X, by the way I write an X and a Y. We usually use X for horizontal and Y for vertical. We're going to be using Y very soon, but for now, let's keep considering motion left to right. It's just simpler, and I'll use X for that. Moving on to the equations, these two equations in the box, these are really important. These are definitions of velocity and acceleration. And we made a distinction between average velocity and instantaneous velocity, where instantaneous has to do with what's currently the velocity at any given moment. How do you do that? You can do it graphically just by looking at the slope of your position time graph. That will give you the instantaneous velocity. Don't make the mistake, I've seen this in labs occasionally, don't make the mistake of trying to find the slope of this brown line by taking 0, 0 and the point you're interested in. Remember that the slope is a tangent line and not anything else. Now, everything I've said so far pertains to the general case of acceleration and velocity in whatever number of dimensions you're looking at. If we want to zoom into motion in one dimension, here's an example of a railroad car that can only move in one dimension, which means left and right, or I might say plus and minus. If you're in that situation, the plus and minus begin to have a meaning, and we've discussed that earlier, right? So plus for position, where you are relative to the origin. Plus for velocity is moving to the right. And for acceleration, there's 4 different cases, as we've discussed at length. For graphs, there's something really nice about the graphs of motion. There's a really nice symmetry, and we haven't been explicit about pointing it out yet. But if you look at these graphs, you'll see that, as you well understand, slope of a position time graph gives you velocity, and as you well understand, slope of a velocity time graph gives you acceleration. And you even know that slope of a velocity time graph, or the area under the curve for a velocity time graph, gives you displacement. So it's not exactly position you get displacement from that. What we didn't say, and we're not going to really study, but I think it's an interesting thing to point out, is that it's also true that the area under the curve of an acceleration time graph gives you change in velocity. Not velocity explicitly, but change in velocity. I won't say anything more about that, but as you study physics, the more you look at that, the more cool that will be. It's just like, it's very clean and neat, and it has to do with the fact that taking position and going to velocity is taking a first derivative in calculus, and going from velocity to acceleration is also taking a first derivative. Or if you want to jump from position to acceleration, that's a second derivative, I guess. Enough about that. let's move on. If you look at this entire poster, this is everything you know already about motion. I'm going to leave that up for a second. If you want to freeze your video and explore it a little bit, you're welcome. And then I will move on to the kinematic equations. Wow, so we haven't talked a lot in this video series about kinematics, or calculating algebraically motion. I'm not going to do an extended session in this series, this video series, but it's a really important topic, and so it's important to include it in your review of motion. If you look at the slide here, you'll see that the kinematic equations can be written in, well, different notation, right? So here is one teacher's view of good notation for 3 kinematic equations, right? There's 3 different equations that are of interest. I tend to use this one on the bottom. I got it from the Giancoli Physics 6th edition. Let me hold that up for you. You may have seen this book. I'm a huge fan of this book. Highly recommend that you browse around, learn what you can. There's a lot of good stuff in there, including page 27, where you will see these equations written. The top 3 are the ones we'll use the most, and they all have meaning that you have presumably studied by now and practiced solving problems. These are vectors, even though they have no arrowhead drawn on top of them. If you look at the lower left of my slide here, I sometimes write vectors with arrows above them to remind us that they are vectors, but as I present to you and as Giancoli presents to you these kinematic equations, there's no arrow written, but it's understood these are vectors and they carry plus and minus signs that have meaning. Okay? So that's as much as I will say about kinematics in this presentation. We're going to study and practice problem solving in kinematics more when we look at up and down motion, which is coming up soon. That is all we have for today.